So, okay, so we're recording now, hopefully. So what we want to do is we want to, so we're doing problem 1. So what's said in the video is that there were 19 staffers and they each tasted 3 different wines, and the video says that almost half, so I assume that means 9, identified the most expensive wine correctly. So we want to know whether people can tell expensive wine from cheap wine. So the first question is, what's the null hypothesis? And actually, like, there could be various null hypotheses. So the one that I had in mind was that they just randomly pick one of the wines and say that this one is the most expensive one. So you could have something more complex as well, where they can kind of tell that the wines are different, but their tastes are different, whatever. But I'm just assuming that they're just, so the null hypothesis is probability of correct guess is just 1/3, right? Because there's 3 wines, they got to choose one of them, so that's 1/3. So this is like flipping a biased coin, which has a probability of 1/3 of coming up heads, where heads corresponds to correct guess. Okay, so now we want to compute the p-value of the null hypothesis using p-binom, make a conclusion about that, right? So probability of correct guess is 1/3. So number of staffers is 19, and number of correct guesses is 9. Yeah. So we want to know how often would we get something that's as extreme or more extreme than 9, right? So how often would you get 9 or more? So this would be, so we want to basically exclude 8 or fewer, right? So p-binom of q is equal to 8, size is equal to 19 because 19 people are answering. Probability is equal to 1/3. That's the probability of getting 8 or fewer correct guesses out of 19, assuming that the probability of a correct guess is 1/3. So this is this much. So that means that the probability of 9 or more is just 1 minus this much. So that's 14%. So we can right away say that the null hypothesis was not disconfirmed, right? So there's not strong evidence against the null hypothesis that people are just guessing, because the probability of getting 9 or more is not that small, it's 15%. Now, what we need to do is we need to also say, well, but actually it would be just as surprising if very few people identified the correct wine, right? So that would mean that people do actually have a way of telling expensive wine from cheap wine. They just need to think about which one they think is the expensive one and then say the opposite, right? So for that reason, we should probably multiply this by 2. You could argue that this is enough, because you could argue that, well, if anything, people should be able to tell expensive from cheap, but they're not going to be confused the other way. But it's safer to compute this. So this means you'll reject less often if you multiply the p-value by 2. And that would be 0.29. So this is kind of probably the more correct approach, right? So the idea here is assuming, so what you expect most is 6, right? And then maybe it looks kind of like this. So this is like the number of correct guesses. So we got, so 6, 7, 8, so we got 9, and we want to compute the probability, this plus this plus this. But then we also want to compute the probabilities on the other side of 6 that are as surprising as 9. So one approximate way to do it is to just multiply this p-value by 2. So that's not going to be kind of the exact correct thing, because it might be, and in fact, it's very likely that there is not a number of guesses that's as surprising as 9 or more on the other side of 6. So we can, in fact, compute it exactly, right? So we can say, let's compute p binom. So let's remember how much this was. So this was 0.14. So the question we're now asking is, well, what's the number of correct guesses that's as surprising as 9 or more? So we can just try it. So we'll say, like, what if we try q equals 3? That's kind of as far away as 9 is from 6. We'll do prob is equal to 1/3. But what we'll get is that q equals 3 is more surprising. So 3 or fewer is more surprising than 9 or more, right? Because the probability is smaller. So small probability, more surprising. So we can try q equals 4. And that's more surprising. So the really kind of correct thing to do if you want to compute it is to say q equals 4 here and add 9 or more. Because here it's like 4 or fewer, 9 or more. That's the probability of getting something as surprising or more surprising than 9. So here you're overestimating a little bit because on this side, so 4 or fewer is 18%. But this is like 16 or something, 14.6. But it's better to overestimate the p-value than to underestimate it, because if you're underestimating the p-value, that means that you might reject a true null hypothesis. You really don't want that. Okay, so we can get the 4 automatically using q binom. And we can say p is 0.146155, size equals 19, prob equals 1/3. And this is just going to give us the 4. Does this make sense? So this is more than I expected last week because we haven't done this last week actually in this kind of style. So what I would have expected is something like 2 times this, or just kind of say 3 is as far away from 6 as 9 is. So we'll just use q equals 3. All right. Questions about this? Okay, all right. So we'll move on. Okay, unfortunately, I can't stop recording, so the recording is going to be for all the questions. So this was problem 1. So let's look at problem 2. So, okay. So problem 2 is about the ratings, right? So what we have from the data that we know about is that wine A got 4.8 out of 10, wine B got 4.8, and wine C got 5.4. Okay. So suppose that here our null hypothesis is that wine B and wine C are on average rated the same. And we want to test this hypothesis. Now, we don't actually have enough data to test this hypothesis without making further assumptions, because we don't know how the ratings are distributed, right? And that actually matters, because if literally all the ratings from all 19 people for wine B were 4.8, maybe they kind of gave like a precise rating, and all the ratings for wine C were 5.4, we would say that's pretty good evidence that those are the actual ratings. On the other hand, if the ratings vary a lot from person to person, then it's possible that kind of for those particular 19 people, the average for wine B came out to 4.8 and for wine C came out to 5.4, but that was just because of those particular people. If other people were rating, because the ratings vary so much, we would say, well, that doesn't mean anything. So we'll see kind of how that affects things mathematically as we solve the problem as well. So in the meantime, we got to try making kind of a reasonable assumption about what the standard deviation of the individual ratings might be, right? So how might we do it? So we know that kind of the implication of our assumption is what the distribution of the ratings looks like, right? So this is going to be the mean. And then this is going to be the standard deviation, right? So the standard deviation can be too large. That's implausible. So for example, if you assume that the standard deviation is 3 and the average is 5, then you're imagining that you'd have ratings of like -1 and ratings of 11. And that's probably not how it went, because probably people just rated like from 1 to 10, or maybe from 0 to 10. But no, but like it's probably impossible to give a rating of -1. It's also kind of implausible just from prior knowledge of how ratings work, that that everyone gave like, so that all the ratings were like very, very concentrated around the mean. So probably not. So what I would do is I would say, well, like what's a sigma that kind of makes sense? Like maybe 1.5 or something, right? So if the sigma is 1.5 and the average is around 5, then most of the ratings are going to be within kind of 5 minus 2 sigma, 5 plus 2 sigma, which for sigma equals to 1.5 would be between 2 and 8. And that kind of makes sense, right? So you'd have like some ratings that are below 2, some ratings that are above 8, but probably not very many. Make sense? So that's the sigma that we're assuming. So now we should be generating the data. So how do we generate the data? So according to the null hypothesis, wine B and wine C are rated exactly the same. Now, in the data, we see that they're rated differently. So we got to figure out, like, if they're rated the same, what would the rating be? And one natural thing to do is to say, well, like, if those are generally the same, and the reason the averages are different is just because, like, those particular 19 people rated the wines this way, right? The natural thing to say is, well, the average is going to be, well, the average between 4.8 and 5.4, so 5.1. Now, in this problem, actually, if you try a different average, you see it doesn't matter for the problem at hand, actually, what you set the average to. The p-value is going to be the same, whatever you set it to. So anyway, so here we just kind of decide on 5.1. So what do we need to do? So we need to repeatedly generate a data set and then compute the difference between the mean for 1A, 1B and 1C, sorry, and see how often it's as large or larger than 0.6. So if the difference is larger than 0.6 often, you would say there's not really evidence that 1B and 1C are different. If the difference between 1B and 1C under the null hypothesis, where there is genuinely no difference, is very rarely above 0.6 just due to random chance, you would say the data that you have is inconsistent with the null hypothesis being true. So, okay. So we'll do like fake ratings as the function. So here, let's give it like so SD might differ between different runs. So I'll give SD as a parameter so that I can easily change this. And I'll say, so wine B, or let's say ratings B. So we'll say that's our norm. So we know that we have 19 ratings. So n equals 19. And we'll say mean is equal to 5.1. That's what we computed. And SD is equal to SD. So we kind of assume that it would be like 1.5 or something like this, but we'll want to see the effect of changing that, right? So similarly, we'll generate rating C. So what we're interested in is the difference between the mean of ratings B and rating C. So we'll do that. Okay. So that's going to be this. So now I can say fake ratings. I'll say SD equals 1.5. That's what we decided on. We see that the difference is 0.8. Now we see the difference is minus 0.7. And so on. So just by looking at this, it seems like a difference of 0.6 is not really indicative for 19 ratings. raters is not really indicative of there necessarily being a genuine difference between the ratings. But OK, so we'll do diffs and we'll do replicate. So let's do like 10,000, doesn't matter. And then we'll say fake ratings SD equals to 1.5. And then we'll just say, well, how often is diffs greater than 0.6? So questions about why this is 0.6? Is this clear? OK, is this not clear? OK, I'm continuing. So we'll get the 10,000 differences, and now we'll compute diffs. And you see that 0.1% of the time, actually, I forgot to do absolute value, because kind of a difference of 0.6 and minus 0.6 are like, one is as surprising as the other. So you see that about 20% of the time, a little bit more here, you see a difference of 0.6 or greater, which means that we cannot reject the null hypothesis because we observe a difference of 0.6 or greater quite often, even if really the means are exactly the same. So that is assuming that SD is 1.5. So if you made a different assumption, so if you said that maybe SD is 0.5, and you don't know from the data because you're just given like the means, you're not given the standard deviation or the actual rating. So if we assume that the SD is 0.5, what you'll see is that almost never is the difference going to be greater than 0.6 under the null hypothesis. So that would imply that there is a genuine difference. Cool. So here, like, you got to make an assumption about how ratings differ for like wine that actually tastes the same. All right, so this is this. I think, yeah, so yeah, and here, yeah, so we are doing this. So here you see that if the sigma is smaller, then you would reject. Kind of the larger the sigma is. So if you make the sigma really large, like you make it 3.5, so you have like negative ratings sometimes, and you have ratings over 10 sometimes, you'll see that the difference of 0.6 is actually pretty small. So more than half the time, you'll get a difference that's actually greater than 0.6 if there is a lot of variability between ratings of the same wine by different people. OK. And so like it's important to understand the intuition here. So the intuition is if you can measure something really, really precisely, then even small differences, and we think about kind of a taste test as a measurement, like how does it taste? It's a 5.1, right? So if you can measure stuff very, very precisely, then even small differences between measurements are going to be quite surprising, assuming that you're measuring two things that are the same. On the other hand, if the measurements are not precise, so if the ratings for the same wine can be all over the place, then a difference of 0.6, for example, assuming that the standard deviation is 3.5, is just not that large. So a different thing that you can vary is how many tasters, right? So let's say that instead of 19 tasters, you have 1900 tasters. So what do you expect to see? So even if I'm not being very precise about how I'm measuring something, but I'm measuring it a lot of time, right? Then the mean is going to be pretty precise, even if the individual measurements are not precise. So that means that larger difference, kind of even a small difference, would imply a significant difference. OK, and I can see kind of how it works out. So I don't know if 1900 is enough, but I suspect it is. No, that, yeah. So yeah, so never is the average rating kind of for 1900 tasters for wine B, 1900 tasters for wine C. Never is the average rating different by 0.6 if the true means are the same. So we can go back and look at why that is, right? So that has to do with the sampling distribution of X bar, right? So if you have X1 and so on up to X 1900, and then you measure X bar, that's the average of those. So that's going to be normally distributed with mean mu, so the same mean as those guys, and variance sigma squared divided by n. So if you assume that sigma is 3.5, then the sigma for the X bar is going to be 3.5 divided by the square root of 1900 in case you have 1900 tasters. So 3.5 divided by 1900 is 0.08. So you would not expect the mean of ratings B to vary by more than twice that, which is why a difference of 0.6 is quite large in this case. Okay.
So does this mean that if like the n in our norm is smaller, then the standard deviation matters more, I guess?
So no, well, so the standard deviation matters the same amount regardless of n. So what this means is that so you'd expect smaller differences between the means if the means are of larger samples. Right? So this is a different null hypothesis. So this is like a different setting where you don't have 19 people rating wines, you have 1900 people rating wines, and you see that there is a difference of 0.6 between the ratings for one wine and another wine. And what we're saying is that for 19 people, a difference of 0.6, like you'd expect that even if there's no underlying difference. On the other hand, if you have 1900 people rate and you have the average of that, then a difference of 0.6 is comparatively pretty large. Okay?
Gotcha.
Okay, all right. So anyway, so this was the solution. So we're doing problem 3.
Hey, can I ask a question really quickly? I put it in the chat, but I'm not sure if you saw.
I did not see it.
So for both 1 and 2, I was wondering, are you assuming that the alternative hypothesis is two-sided? And if you are, why?
Yeah, so here I'm assuming, yeah, so we have not really discussed one-sided hypothesis yet in class. So by default, you should think about two-sided, and usually that is my advice in general. So like you need to like have a really, really good reason for the hypothesis to be one-sided. So like if you think that, if you think that wine C can only ever be better than wine B, there is no way that it would be worse, then you might be justified in doing a one-sided test.
Okay.
But like it's hard to imagine even kind of hypothetically how you would be like extremely convinced that wine C can never be worse than wine B, right?
Okay. Okay, thank you.
Okay. So you might imagine, so kind of in some situations you might, so kind of a situation in which you might imagine that the difference can only go one way, right, is like, let's say that you're weighing something on a scale and then you're putting on like another object on the scale. So you would say, well, like this would never make the weight smaller, it can only make the weight larger, right? But that's basically so it's quite rare, and I think kind of a lot of the time people just inappropriately use one-sided hypothesis there. So the implication usually is like the p-value is just twice as large if you use a two-sided test, which means that you're less likely to reject. And like usually kind of generally we're more concerned about improperly rejecting a null hypothesis than not rejecting it when we could have done. So okay, so problem 3. So here we're asking a slightly different question. So we're saying, are any of the ratings different? Sorry. Right. So we actually, like, it would be inappropriate to look at the data and then say, well, like B and C look different. Can we test whether that's statistically significant or not? That's not appropriate. So that is because if you look at like 10 wines that are exactly the same, just due to random chance, you'll have a pair of wines that are different. But, well, like you look at the data and you select the pair that's different. So the p-value that you compute then would not be valid. The reason it would not be valid is you can always pick something that's statistically significant just due to chance if there is a lot of stuff to pick from, okay? So the way it works, ideally at least, is you formulate a hypothesis, then you collect the data, and then you test the hypothesis. Can't formulate the hypothesis after you collect the data by kind of cherry picking the large differences. So that means that unless we had the hypothesis that 1B is different from 1C prior to the experiment, which we actually might have done in this case because we have information about their prices, what we can ask is like, are any of the ratings different? Okay. So how is that different from the previous one? So in the previous one, we are just computing the difference between ratings B and rating C. So in the case where we don't particularly know that we need to compare B and C, because remember, those were the wines that were different in the data, we generate wine ratings A as well. Right? And we'll say, okay, so we have ratings A, ratings B, ratings C, and we want to know how often is the range 0.6 or more. So if the range is usually not larger than 0.6 when all the wines are the same, then we can say, well, a range of 0.6 is surprising. That indicates that at least one wine is different from another wine. On the other hand, if the range is usually large, then we can do that. So, okay.
Quick question.
So yeah.
Sorry, I was just wondering why we're still using the range 0.6 if we're formulating a hypothesis before we're collecting data?
We are formulating a hypothesis before we're collecting data, and the hypothesis in this case is not all the wines are the same, right? So
right. So why are we still using 0.6 as a range?
Because that is what we observed, right? So so we formulate the hypothesis. We are saying we expect to see, so the null hypothesis is all the wines are the same, so we expect a small range. We observe 0.6. So our question is now, is 0.6 large enough for us to conclude that the wines are not all the same, right? Because 0.6 is what we actually observed, so we need to know whether that's large enough. Does that make sense? So the hypothesis was formulated prior. The hypothesis was not, it's going to be greater than 0.6. The hypothesis is the range is not 0. Okay, but then we observe 0.6, and we're asking, is 0.6 different enough from 0 to justify saying that not all the wines are the same? Does that make sense?
Yes, thank you.
Okay. So I'll make a vector that's going to be ratings A, ratings B, and ratings C. And now, so to compute the range, I'll just do like max ratings minus min ratings. Make sense? So I just put all, sorry, this is mean, of course. So that's going to be like this. So ratings, for example, might look like this. And then max minus min might look like this. Okay, so this is for a very large standard deviation. So we'll do the thing again. So we'll set the SD back to, I think we said like maybe it's like 1.5. And we'll ask how often is the range greater than the range that we actually observe, which is 0.6. And the answer is happens all the time. Okay. So was there, so this, okay, this is unfortunate because I deleted problem 2, but people can just rewind the video. So this is now problem 3. Okay.
Wait,
So-
for problem 3, could you say one more time why you did the max minus the min?
Well, that's just because that's what we wanted. So find the probability the range of the average ratings for the 3 wines is greater than or equal than 0.6, right? So the range is the max minus the min. That's what the range is.
Oh, okay, I didn't see that. Thank you.
Okay. So let's now do problem 4. So that's the sample size that's needed to detect a difference of 0.6, right? So what we see here is that if you just have 19 tasters, you would expect a range of 0.6 like all the time, right? So one question that arises is, well, like, let's say that genuinely the difference is 0.6, right? So then how many tasters do we need in order to, when we detect a range of 0.6, to say that's actually genuine, right? So in other words, we want the sample size n such that we usually would not see a difference of 0.6 when the true difference is 0. Okay, so just copy this. So here I'll change this function a little bit to also have take n raters, and I'll put n raters here. Okay, and now so here I'll put like n raters, and here, like, let's start with like 40. So for 40 raters, how often would we see a difference of 0.6, right? So the answer is 17% of the time, so that's still large. So let's try like 100. Okay, 1% of the time, so that's good. So let's try like 80. %3 of the time. So let's say 65. So 65 gets us just over 5%. So maybe we bump it up to like 75 and say, okay, that's good. So that's not quite enough, right? Because we also want to say, okay, so if we get a difference of 0.6 with 75 raters, then we know that that's going to be considered statistically significant. But how often would we get this difference if the true difference is 0.6? So I'll bump one of the wines up to 5.7, and I'll keep the others at 5.1. So this would be fake ratings diff. And now I want to know how often is the difference going to be greater than 0.6 so that I can say that it's significant. So I'll just do fake ratings.diff here. And I see that 65% of the time, I'll observe a difference that's 0.6 or larger. So this is not amazing, but it is what it is, right? So if I increase the number of raters, it's not going to be like that much better. So that's going to be 67. So that means that if the genuine range is 0.6, then I'll be able to reject the null hypothesis that all the wines are the same 67% of the time. Okay. And I will be able to reject it because under the null hypothesis, you would not expect to see a difference of 0.6 or larger for like more than 75 raters. Make sense?
I think you have n raters as being 175.
Yes. So I increased it a little bit in order to increase this. That did not help much, so it just gives a more accurate thing. So yeah, so kind of 75 is like the kind of answer that we'd be looking at.
Could you explain again? So just looking at, or I guess just trying to find the probability of n-raters where it's significant to find a difference of 0.6 isn't enough. So you also have to look at changing the mean by
well,
0.6?
so because like the other question as well is like, let's say that obtaining a difference of 0.6 means that you found kind of a significant difference. The other question is, how often would you get the difference of 0.6, right? Because if the answer is not very often at all, then it's not useful that you'll be able to reject, right? So this is saying 67% of the time will actually get a range of 0.6 or greater. If the true situation is that A and B are both 5.1 and A and C, sorry, are 5.1 and B is 5.7.
Oh, okay.
Okay. Okay, so that's that. So let me just make sure that I recorded. Do people have other questions? Sorry, so, okay, so I'll leave this meeting so that they'll have a recording that's ended, and then I'll come back in like 30 seconds.